10 years ago, one of the main problems with Java performance was GC pause times. Today, when running ZGC, the pauses are so short, they are no longer noticeable. In this session, we will take a walk down memory lane and see how ZGC have evolved and made Java much more suitable for low latency workloads. With that, I want to welcome you all to this presentation. My name is Stefan Johansson. I work in the Java platform group at Oracle, and my main focus is garbage collection. I've been doing this for the past 13 years, and the main focus is the JavaOne garbage collector and the ZGC garbage collector, but I also care deeply about performance in general. So before diving into ZGC, let's talk a bit about performance in general. So what is good performance? Well, that's a very general question, and it's kind of like asking how long is a rope. It all depends what you care about for your use case and from what aspect you're looking at things. So in the Java platform, we care about performance from many different angles. For example, we have just-in-time compilation. We care deeply about performance when it comes to that, and my colleague Roberto will be talking about that tomorrow morning in the auditorium downstairs. And we also care about performance when it comes to startup and warm-up. We address that in Project Laden, and right after Roberto's talk about Git compilation, Dan will talk about Project Laden, which is all about startup and warm-up performance. But I am a garbage collection engineer, so I care mostly about GC performance. So if we change the question to what is good GC performance, can we answer this a bit better? Well, it still depends, but we usually talk about three different aspects here. We have throughput, latency, and footprint. So let's look a bit closer at what we mean by those. So throughput is mainly the number of transactions that you can complete in a fixed amount of time. And from a garbage collection point of view, what will affect the throughput performance? Well, one big thing is if you do concurrent GC work. So that is GC work that happens at the same time as your application is running. That will affect the throughput. Many and long GC pauses might also affect the throughput performance of your application. And then we have read and write barriers. This is very efficient and specific code that the GC needs to be able to perform its work. That is executed every time you access something in the heap. Then we have latency, and this is more about the duration of a transaction. And then again, what will affect this? Of course, the main thing here is long GC pauses. Another thing that will affect latency performance is if the application threads have to help out to do GC work, and that can happen if you have a concurrent garbage collector. We also have something called allocation stalls. In OpenJDK, ZGC is the only garbage collector that can have allocation stalls. But if you see them, you should try to increase the heap size, because the reason for allocation stalls is that the application allocates memory faster than the GC can reclaim unused memory. And then large allocations is also something that might affect the latency of your application. So if you care about short and deterministic response times, you should avoid large allocations in your critical path. The last aspect we talk about is footprint, and that is mainly the overhead for a transaction because of the GCs. So we talk about that in terms of memory and CPU resources. And then, of course, the things that affect that is the additional native memory that the GC requires to do its work. And this is in terms of like data structures to keep liveness information and things like that, so that the GC can work properly. And of course, the GC work requires CPU resources, so that's the overhead from a CPU point of view. So with those things defined, can we better answer the question, what is good performance? Well, it still depends on your use case, but this makes it easier to reason and talk about GC performance. But it's always, depending on your use case, different garbage collectors work differently. So if we look a bit at how garbage collection works in OpenJDK, well, we don't have a perfect garbage collector, so we don't have anything that solves everything perfectly. Instead, we have multiple garbage collectors. For example, we have the JavaOne garbage collector, which is the default garbage collector, and it tries to strike a really good balance between all these different aspects. So it provides great throughput, have controllable latencies, and pretty low overhead. But then we also have more niche collectors that tries to achieve better peak performance for specific use cases. And as mentioned, if we go back 10 years, one of the biggest problems was long GC pause times. And the main reason for this was that most of the work was done in the GC pauses. We had something called mostly concurrent collectors, G1 and CMS, but they still did a lot of work in the GC pauses, leading to longer GC pause times. So it was time for something new. And this is where ZGC comes into the question. So if we take a look at the initial goals for ZGC, it wanted to be the best possible low latency alternative. We wanted the GC pause times to be below 10 milliseconds. We also wanted ZGC to be very scalable. It should be able to handle terabyte-sized heaps. And we wanted it to be easy to use. So minimal amount of configuration should have to be provided by the users. Because in the past, we had seen a lot of garbage collectors where you had to specify maybe 10 flags to get a good performance for your specific application. So to meet those goals, the guiding principle for ZGC is concurrency. So ZGC is a concurrent garbage collector, and it really tries to have very, very short GC pauses. And this is to make it suitable for low latency workloads, and in turn make Java suitable for low latency workloads. There are still pauses, and we made sure that those pauses don't scale with the heap size, because being able to meet those pause time goals and still being able to support very large heap size, we can't have the pause time scale with the heap size. So that was something very important in the beginning of the ZGC project. And then, of course, most of the GC work should be done while your Java application can still continue to run. So we do the liveness analysis, that is figuring out what Java objects need to be kept around. Then we move those objects to new locations to be able to free up memory, all while your Java application is still running. And then, of course, we also free the memory concurrently with the Java application running. After a number of years, a very big part of this foundation was done, and in JDK 11, ZGC was released as an experimental feature. Up to this point, a lot of the work was focused on ZGC, but we also spent a lot of time making sure that the JVM was suitable to handle a concurrent garbage collector. We implemented some building blocks, for example, a possibility to synchronize all Java threads without having a GC pause. And that is very important because we still need synchronization, but we don't want to stop all threads at once. And we call that handshaking. In JDK 11, ZGC was only available on Linux 8x6, but the performance looked very promising. So let's take a look at the GC pause times. But before looking at the actual numbers, I want to introduce SpecJDB 2015. This is an industry standard benchmark, and I'm going to use this throughout this presentation. It's developed by the Spec organization, and it simulates a web store. So pretty real-world-like. It's still a benchmark, so it's not a real-world application, but at least it tries to simulate something that is used in the real world. The good thing about this benchmark is that you can configure it in a couple of different ways. We have a compliant mode, which gives benchmark scores that can be used to compare JDK releases, different garbage collectors, and different systems as well. But then you also can configure it with a fixed load. So you set a predefined number of transactions that you want to push through the system. And this is very good if you want to look at metrics. So for example, GC pause times. So in this first chart, we're using SpecJDB with a fixed load. And we can see that the average pause time in JDK 11 in this benchmark was around 1 millisecond. And the longest GC pauses were slightly below 5 milliseconds. And to put this into perspective, let's compare this to how G1 looked at the time. And you should note that the scale is completely different here, and that the longest G1 GC pauses are 250 milliseconds. This makes G1 look pretty bad, but actually G1 is doing a really good job here. The default pause time target for G1 is 200 milliseconds. So we can see that almost all the GC pauses are below that default goal. And if we would look at G1 in JDK 25, all of the GC pauses would be below 200 milliseconds. So we actually achieved to shave away those worst case outliers with G1 nowadays. But still, from a low latency perspective, ZGC with its short pauses, it's a really, really good alternative. So, as mentioned, most of the foundation was in place at this point. So we started to refine our goals. One obvious thing, not easy, but was to do even more stuff concurrently. So one thing that was even missing in the experimental release was class unloading. So the ability to unload classes. That was implemented in JDK 12 in the concurrent phase. So being able to unload classes while your Java application is still running. Next, we had concurrent thread stack scanning, and that has to do with liveness analysis. So to be able to figure out which objects on the Java thread stacks that needs to be kept alive, or which routes, which objects on the thread stacks are routes that points to objects in the heap that needs to be kept alive. We implemented that in JDK 16 to make it possible to figure that out while the Java application is still running. And we also worked hard on making sure that we had a wider platform support, because if you have a garbage collector that you want to be fully supported, you need to support all the platforms. So we made sure it worked on Linux, Windows, and Mac OS, on x86 and Arch64 as well. ZGC can be used on a few more platforms, but these are the platforms that we support at Oracle. Another thing that we spent a lot of time here was to improve the out-of-the-box behavior. So ZGC, as I mentioned, we wanted it to be easy to use. In the early days, there were some configuration things that wasn't that convenient, so we worked hard on improving those things as well. And we made sure that the heuristics were also better to avoid user having to set the number of GC threads, for example. Getting all these pieces together made ZGC production ready in JDK 15, and by the time of JDK 17, the GC pauses were only used for synchronization reasons, so no real heavy GC work was done in the GC pauses anymore. At this point, the low latency goal was more or less achieved, at least from a pause time perspective. The next big problem to solve was the scalability. And at this point, ZGC collected the whole heap in each garbage collection cycle. And for many use cases, this is not efficient enough. The solution to this is what we call generational garbage collection. Generational garbage collection builds upon the generational hypothesis, which says that most objects are only used for a short period of time. So how can we make use of this? Well, if we separate objects depending on their lifetime, we put newly allocated objects into the young generation. Then we put long-lived objects into the old generation. So that's objects that's been around for a couple of young generation collections and seems to be sticking around. This is a way to reduce the cost of GC by moving fewer objects. And the idea here is that if the generational hypothesis holds true, that means that very few objects in the young generation will actually be live and have to be kept around. So we move fewer objects, we collect the younger generation more frequently, and then of course, sometimes when the old generation fills up, we have to do old generation collection as well. Those are slightly more expensive, but since we do them very seldomly, the overall cost of doing GC is reduced. So to make ZGC scale, one of the most important things here was to implement generational collections for ZGC. And we spent about 2 years focusing only on this. And this is very important because it allows ZGC to handle much higher allocation rates and also to avoid allocation stalls, even with smaller heaps. So this in turn leads to making ZGC suitable for a lot more workloads because you don't require as much heap and ZGC is not using as much CPU as it did without generational collections. We introduced generational ZGC as a different option. This was mainly used to allow users to migrate over time and for us to get feedback if users saw any problems with the generational collections. So in the initial release in JDK 21, you need to enable generational ZGC with the flag cGenerational. So in JDK 21, we have generational ZGC. And again, if you're using JDK 21, make sure to enable the generational collections. They are fully supported, and we think that is the way to go. And especially looking into the future, since then, we've been prepared to make ZGC easier to use and also to make it possible to implement new features for ZGC. And a big part of this is to make sure ZGC is only generational or always generational. So there is no longer need for a flag and the non-generational mode has been removed. And this is basically because if you have 2 versions of a collector, when you implement a new feature, you will have to implement it for both modes. So, and we didn't really see anyone saying that the non-generational mode was needed. So yeah, the end goal was always to just have a single version of ZGC. And we also worked hard since JDK 21 on improving the internals. One big thing was that we made the handling of free memory much more efficient. So in the past, we sometimes saw problems with fragmentation issues for specific workloads. That is no longer an issue for ZGC. And we've also implemented ahead of time object caching support, which makes ZGC play much better together with Project Leiden, which, as mentioned, is another very important project in OpenJDK. So now in JDK 26, which was released today, yay, we have a great collector and it's ready for the future. We have quite a few ideas lined up that we want to address going forward. I'm going to talk about one of them a bit later in this presentation around automatic heap sizing. But before we do that, let's take a look at the current status and the current goals of ZGC. So their goals are slightly refined from the initial release. So now we want the pause times to always be below 1 millisecond. And if we look at how we handle those goals, from a low latency perspective, I would say that we tick all the boxes. The pauses are just there for synchronization reasons, to make sure that the application threads and the GC threads agree on what phase we're currently in, if we're gathering liveness information or if we're moving objects around. Scalability-wise, with generational ZGC, things looks really great. We can handle terabyte-sized heaps. ZGC is usable with just a few hundred megabyte heaps, and things looks great from this point of view as well. When it comes to the auto-tuning part, we tick most of the boxes, but we still tell the user to set a heap size. And that might sound easy, but setting an optimal heap size is not as easy as it sounds. It requires a lot of information, and yeah, we're going to dig deeper into this later on in the presentation. But first, let's take a look at performance. So is ZGC providing good performance? Well, if you ask me, yes. It's especially great for low latency workloads and applications where you care about short response times. So compared to G1, the GC pauses in ZGC is no longer noticeable. They are only there for synchronization reasons. And to recap a bit, in ZGC, everything that has to do with garbage collection is done concurrently with your application. determining liveness, moving objects, and freeing up stuff. You might recall from earlier in the presentation that I said that if you do concurrent JDC work, that might affect your throughput performance. And this is true. And that is why we work very hard on making sure that the concurrency overhead is low. In many cases, you're not using all the CPU resources on your system because you don't want to do that, because you get unpredictable latencies in many cases if you have a very high CPU usage. So in those cases, using more CPU to do concurrent JDC work might not be a very big problem and might not affect your throughput performance that much. Still, we work hard on making sure that the concurrency overhead is as low as possible. One part in this is returning memory as quickly as possible. This is also very important to avoid allocation stalls and keeping the heap overhead low. We also want to make sure that the CPU overhead is at a minimum, and two very important parts to this is to have very efficient barriers and of course having efficient garbage collection algorithms. In ZGC, we have a feature called colored pointers, which is very important to achieve those things. Colored pointers is basically metadata bits that we have in the object pointers. And with those metadata bits, we can figure out pretty cool stuff. For example, with respect to returning memory as soon as possible, with ZGC, we can reuse memory as soon as an object has been copied to a new location, because all pointers to the old location have metadata bits that tell us that this needs to be changed. This pointer is no longer valid because the object has moved, so we need to update this pointer. So we can reuse memory as soon as the object is copied. And that is unique to ZGC and OpenJDK because all the other garbage collectors need to update all the pointers pointing to the old object before the memory can be reused. So we can do a lot of cool stuff with the colored pointers. If you want to know the gory details on this topic, my colleague Eric Östlund has done a great presentation about this. It's available on the Java YouTube channel, so please check that out if you want to know the details. So we've looked at the JDC pause times in JDK 11. Let's see how they have progressed over time. And if we look at JDK 17, it's hard to see. Same is true for 21 and 25. So let's zoom in a bit. We can see here that in JDK 17 and 21, both those bars are all with the non-generational mode of ZGC. We still see very impressive short JDC pause times in the realm of a couple of 100 microseconds. They are even shorter, the worst case latencies, with JDK 25 and generational ZGC. What should be noted is that when the JDC pauses are this short, it's not that important to improve them even more. So even if the worst case pause here is maybe, if you look at the percent, much shorter, that's not that important because they are not really affecting the application response times because they are so short. So we've seen the evolvement of ZGC and we have seen that the JDC pauses are great. Another thing that might be interesting is to see how ZGC compared to JavaOne when we look at performance from a bit broader terms. Comparing JDCs is always problematic because depending on how you do it, it's very easy to favor one or the other collector. I'm going to use SpecJBB 2015 to do this comparison. And now I'm going to use the compliant mode, so not the fixed load. And the compliant mode gives you two scores. It gives you a throughput score, which is basically the maximum number of transactions that you can push through the system with a given garbage collector. And then we have a latency score, at least I call it a latency score. It's actually throughput, but with some latency constraints. So we're looking at the P99 response times for a different set of SLAs, and we see how much can you push the system while still maintaining these response times. So for example, JDC pauses will really affect the latency scores. So from a JDC point of view, this is a very, very interesting score. The throughput score doesn't only show the improvements that we've done to garbage collection, it shows kind of the improvements that we've done to the whole Java platform. So yeah, from a JDC point of view, the latency score is more interesting. I do run it with multiple heap sizes, and this is to avoid favoring one or the other collector. If you use a smaller heap, that's going to be better for G1. If you use a larger heap, that is probably going to favor ZGC. So we're going to look at scores for multiple heap sizes, and we're going to see how the scores are affected. So before doing comparison, let's look at the application throughput for just ZGC and see how it has progressed over the years. So we're using JDK 11 as the baseline, so the experimental version back then is at 100%, and going to JDK 17, we can see a significant boost in throughput performance for ZGC. Not much happens going to JDK 21. Here it's the default out-of-the-box behavior, so non-generational ZGC. And the big boost comes from moving to JDK 25. Again, the throughput score here also affected by improvements done to JIT compilation and other things in the Java platform. But to see the impact of GC, we can switch over JDK 21 to make use of the flag C generational, and we do see a boost in performance there as well. But the best possible performance is with the latest possible release in most cases. So let's try to compare G1 and ZGC. Now I'm using G1 with an 8 GB heap as the baseline. And if we increase the heap, we do see a slightly improved score for G1. Going up to a 31 GB heap, an even better throughput score. The reason I'm using a 31 GB heap here and not a 32 GB heap is because G1 makes use of a feature called compressed object pointers, or compressed OOPs. And this allows G1 to have smaller objects, allowing it to have more objects in each garbage collection. And for a stop-the-world garbage collector like G1, it's very important to have as few garbage collections and as short garbage collections as possible. So being able to push more objects into each collection is very important. The drawback is that this is only usable up to slightly below 32 GB. So going to a 64 GB heap, we don't see much improvement in the G1 score. If we then start looking at ZGC from a throughput performance point of view, doesn't look very impressive for an 8 GB heap. We should keep in mind that ZGC is not aimed to have the best possible throughput performance, and this benchmark with an 8 GB heap, it's a pretty rough use case for ZGC and a concurrent garbage collector. Increasing the heap size to 16 GB, we do see a big boost in the throughput performance score, and going to 31 GB, ZGC is starting to perform pretty good. We see a slight increase going up to 64 GB as well. ZGC does not make use of compressed OOPs. Instead, ZGC has the colored pointers. And so that's why it still sees a slight boost. But here there are other things in the system that prevents the throughput score from being much, much higher. But still, the gap between G1 and ZGC for large heap when it comes to throughput performance is not that big. But maybe more interestingly, when we're looking at ZGC, is the latency score progression. So again, using JDK 11 as the baseline, see a very similar pattern here. Not much happens between 17 and 21. And again, a big boost going to 25. Going to show you the similar thing here, that you do get a boost with the generational mode for the latency score as well. But now let's compare ZGC and G1. Again, using G1 with an 8 GB heap as the baseline. When it comes to the latency score for G1, between 8 and 16 GB, you don't see an improvement at all. You see a small improvement going to 31 GB, and again, a small improvement to 64 GB. The reason for this is the G1 GC pauses are not getting shorter because you increase the heap size. And the GC pauses really affect the P99 response times in this benchmark. So the reason we see a better score with 31 and 64 GB heaps is that we're able to push the GC pauses further apart. So more transactions can be processed without being hit by GC pause. So if we instead look at ZGC that basically has no pauses, we can see that even with an 8 GB heap, we're almost able to push as many transactions, almost as many transactions with great response times as JavaOne can do. Going to a 16 GB heap, we start seeing the real strengths of ZGC, and the strengths grow bigger the larger we grow, because we can space out the GCs using more CPU resources for processing transactions, and we really see the strength of ZGC when it comes to looking at the latency score. So this was it when it comes to performance. Now let's take a look at what we have lined up for the future. And as mentioned, the project that I plan to talk about is automatic heap sizing and reduce the need for configuration even more. So we want to remove the need to set a specific heap size. And the main thing here is it's much harder than it sounds. Like, you just set a memory limit. How hard can it be? Well, you need to take so many things into consideration. You have, like, is your application using an off-heap memory? Do you have other processes running on your system in your container? How much memory is the JVM itself using? I mentioned that we have some overhead, that the GC is using memory. Well, the Git compiler is using memory as well. There are so many things to take into consideration to set an optimal heap size. So what people do is that they set something slightly lower and then check out if it works, and otherwise increases or decreases it a bit. So our plan here is to heuristically figure out an optimal size, trying to balance the CPU and memory usage. If you looked at Ron Pressel's presentation earlier today, you understand more what this is about. If you didn't watch that, go and watch it on the Java YouTube later on. It was very interesting. And we're also going to consider the overall usage in the environment. So if there are other things running, we might have to decrease the heap size because we're sharing the system. We might be a container in a multi-container system and things like that. And the end goal is that the only configuration needed for using ZGC should be to enable it. So just enable ZGC, basically. To show you how we plan this to work, I'm going to do some kind of demo, or at least simulation. We're going to simulate scaling out, and the scenario is that we have, again, multiple SpecJBB 2015 instances running a fixed load. So we have 3,000 requests per second for each instance. And then we scale out from one instance to 4 instances and then back, and we see how automatic heap sizing can handle this. The system I'm running this on is a 32 GB machine with 16 virtual CPUs. I'm using a very simple C group setup when it comes to container, and I'm not setting any limits on the containers. This might not be what you do today, and that's because it doesn't really work today. You need to set the limits and you need to set a heap size. Our thinking is that if we get automatic heap sizing correct, you won't need to set any limits in the future, so that you can utilize the resources on your system as good as possible at all times. So I'm using a few metrics here. I'm gathering them using JFR, and the main metric is of course the heap size, but I'm also looking at the application response times that I can get out of SpecJBB 2015, because you want to see how response times are affected by growing and shrinking the heap size. So let's do a demo. Awesome. So since looking at machines and instances running is almost as fun as watching paint dry, I've run this ahead of time, and what we're looking at now is kind of a simulation of those runs. So we have 2 charts here. At the bottom, we have the total usage on the system. So the red line is the total memory usage. The green line is the current CPU usage. And in the upper chart, we will see the different instances. The first instance here is with the orange color, and the line is its heap size, and the dots are the current response times. And that's connected to the right axis, which is also a logarithmic axis. And we can see here that it starts out with a very small heap size and it rapidly increases to be able to maintain low response times. And nothing else is going on in the system, so we can use basically as much memory as we like. If we continue the simulation, at some point we start a second instance. We kind of see the same behavior here. We rapidly increase the heap. But in the lower chart, we're starting to see that we have a pretty high memory usage now. So they are starting to pan out, and they are also seeing that their CPU and memory usage relation is kind of telling it, well, I probably don't need to increase my heap size anymore because I'm not spending that much resources, CPU resources on garbage collection, so I don't need more heap memory. If we continue running, we will start a third instance at some point, and now is when things start to get interesting. Now we have such a high memory usage on the system, so we're not able to increase the heap size as rapidly as we did with the first two services. And the first two services realizes that, whoa, a lot of memory is needed on this system, and maybe we can't use this much. So they start to decrease their heap sizes, which in turn leads to the third instance being able to increase its heap size and starting to get better response times again. But we can see some outliers in the beginning there for the third instance. And if we look at the lower chart now, we see that we are at a very high usage when it comes to the memory. I said that we're gonna scale out to 4 instances, and yeah, now things are starting to be pretty bad. And I wouldn't encourage any of you to run like this in a production system. This is way too heavy load for this system, but it's kind of interesting to see how automatic heap sizing handle this case. And we can see here that we can zoom in a bit maybe, and we do see that the heap sizes are kind of converging towards using more or less the same. We do see that the P99 pause times aren't that good anymore. So yeah, we probably shouldn't scale out this much, but if we continue to run stuff, at some point instance number 4 is going to stop, and we can see that then the heap sizes scale up a bit and the response times go down. As instance 3 stops, we can increase the heap even more for the 2 instances, and in the end we only have a single instance running and it uses as much memory as it sees fit. So I think this pretty well shows where we're aiming. It's a bit of a different view to look at things. And I mean, you could have supported running 4 instances on this system in the past as well. But to be able to do that, you would have to configure the heap size, probably somewhere around 5.5 to 6 gigabytes per instance, because that is about how much they can use when they're all running it together. I actually tried running this with JDK 26 without automatic heap sizing because it's not part of a release yet. And actually we're running out of memory on the system then, so things aren't looking great. So today you need to set the limits, and when you do set the limits, when you're just running one instance, you're going to limit that one to just use 6 gigabytes on the 32 gigabyte host that you paid for. So you're not really utilizing your resources as good as you should. So with automatic heap sizing, we really think that it will help people it's going to be easier to use ZGC, and you will utilize the resources that you paid for in a better way. So with that, I'm gonna head back to, this worked out of the box. Yeah, so the only thing left in this presentation is the key takeaways. So what's the most important things that I told you? Well, Java is great for low latency workloads. And if you care about short deterministic response times, you should really be using ZGC. And remember to upgrade to the latest possible JDK for your specific application, because as you've seen, you get a lot of free performance benefits by just upgrading and using the most recent release of Java. And with that, I just want to thank you for listening, and I will be taking questions.
For the presentation. had to try to experiment with softmax heap size, and we still have to set it, but it will be how.
So yeah, of course. So you're meaning if I'm using softmax heap size instead of automatic heap sizing?
Configuring a max.
Yeah. Yes, there are means in the current JDK that could probably make things work better. In this experiment, like a lot of the time when I do experiments, I want to see the out-of-the-box behavior. So I don't want to set additional things. But softmax heap size is certainly something that you could use to allow for like using a larger heap when nothing is there. But we also let the softmax heap size, we will aim for that. We will not go over that unless we need to. So it will still keep the heap at that size. So I wouldn't say that softmax heap size is not a substitute for automatic heap sizing. It's like, would it really? I don't think so, because in that case, it would help if the system, like if it's loaded to not, it would push above if it actually needs to, but it wouldn't push above just because it can, basically. But yeah, it would help if the workload is rough enough so that you need more heap. And yeah, in this case, but it still, you wouldn't utilize as much of the memory. But yeah, that's a good point. It could help. Yes. Yes. So the question, I should repeat that, is if we have a JEP for G1 as well to do automatic heap sizing, and are we doing this work together? There are, of course, collaborations. ZGC will probably be the first one with this released, and we will learn from that to G1. There are differences since ZGC is a concurrent garbage collector and basically has no pauses. ZGC doesn't have to take care about like, will this increase or pause if I increase or decrease the heap size? G1 will have to take those things into account as well. So there are differences. Of course, we will try to share as much as possible, like how we monitor the system and things like that. And we will work hard on making sure that they work good together so that you can run G1 with automatic heap sizing alongside ZGC with automatic heap sizing. But there are differences, and yeah, hope that helps. Yes?
Do you also?
Yes. So like in ZGC, everything is done every. So again, the question is, do we scale down the concurrent number of GC threads? So we're going to use as many GC threads that we see fit in the current state of the system. So if we can get away with just using one concurrent GC thread, we will do that. If the memory pressure is high, so we need to free up memory faster, we will scale up the number of GC threads. So hope that answers your question. The question is, how do we reduce the stalls, basically? So being able to do garbage collection more efficiently, for example, with generational collections, so we can free up memory and returning it so that the application can use memory, is the way to reduce the number of allocation stalls.
Application to JVM or OS?
Come again?
Where you are returning the memory is to application or is OS?
No, to the application. So yeah, sorry, that should be clear. So when we talk about, in this case, when I'm talking about returning memory, that's returning memory so that the application can allocate. We're not uncommitting memory so that it can be used by the system. In the case of automatic heap sizing, when we decrease the heap size, then we're uncommitting memory so that someone else in the system can make use of the physical memory. No, so I do actually think that we are above 75%. Like the measurements I'm doing is with JFR, and I didn't it's not real-time measurements. So it's like points in time. And if I the CPU usage is very high at that point, and the peaks are certainly higher than 75%. No, so there are both compressed object pointers and compressed class pointers. So those are different things. Oh, again, the question was, is compressed object pointers and compressed class pointers more or less the same thing, but they handle different things. But the main idea is to make sure we only need 32 bits to fit the pointer to a class or to an object in the heap. Very good question. So the question is, did I configure G1 with a pause time target in the latency comparison? And the answer is no. I could have probably increased the G1 latency score by setting a pause target. That would likely have decreased the throughput score. So basically, again, I wanted to do a comparison It's always hard to do a completely fair comparison, but this is an out-of-box comparison, basically. So we could improve the J1 latency score by setting a lower pause time target. That's a good observation. Yeah, so when it's just an 8 GB heap, like we don't have really enough headroom for ZGC, so we do we more or less GC all the time, and when you have a concurrent GCing all the time leaves less CPU resources to the application, so we're not able to push as many transactions through the system. But as we increase the heap size, we don't have to garbage collect as frequently, and then more CPU resources can be used by the application, increasing the throughput. So how we do the liveness analysis? So the question is, do we do a liveness analysis the same way in J1 and ZGC? Kind of. All the GCs in OpenJDK is what we call tracing GCs. So we start off with a well-known set of routes, and then we trace those routes to figure out which objects need to be kept around. The difference is that ZGC does this liveness tracing concurrently, always. J1 does this liveness tracing in a stop-the-world pause for the young generation and concurrently for the old generation. So that's basically the mostly concurrent part of J1, is that we do liveness analysis concurrently with the application for the old generation. No, it's not that easy. Again, it all depends on the specific use case and the specific environment and what you want to achieve. If you care about short response times, often you have a microservice, you're not pushing the CPU usage on that server to 100% in that service. So it might be possible to run ZGC with as little as a few hundred megabytes of heap if you have the generational mode in JDK 25. And that it all depends on the specific circumstances for your use case. So you can never say something like, oh, not much time, something like that. So you should always try out multiple GCs. That's my main answer to that, I think. Yes.
Is it more about the headroom or the overall?
Yeah. So so the question is it more about the headroom? And for ZGC, yes. So if there is enough heap room for ZGC to be able to finish the concurrent garbage collections in time, ZGC is basically usable for all workloads. Perfect. Right on time. Thank you for all the good questions. Happy to talk in the hallways if you have more questions.